Hello, this is Lianos. I'm a physics teacher with ATS in Align, and in this video we'll try to solve question 2 from the 2023 AP exam in mechanics. We scroll down to the exam paper and we see the basic constants and units and list of formula and the basic tips for calculus and geometry in case we will ever need them. We see question 1 that we solved on the previous video, and we continue to question 2, which from what I see is slightly unusual. We have, if I remember correctly, this is a torsional pendulum, and indeed this is a torsional pendulum. Basically, it is a pendulum that is supposed to rotate left and right when we turn it. Now, this is not common material for the AP mechanics, like we are using the simple pendulum in AP mechanics. However, we'll see how we can answer this. A student is making a torsional pendulum by suspending a disc and with a radius, and then we are giving the rotational inertia, and we find the period. Okay, we don't know any formula for the period for this, but from what I see, the period is given below. And we attach more discs later, and later we attach a second disc, and later we attach even more discs to get a final value of n identical discs. The n could be 3, 4, 5, until we get to 10 identical discs from what I see. And using the rule that the period of the torsional pendulum is 2 pi root of I over k. I don't know exactly what the k means, but I guess that it means some kind of constant, that it is not defined from what I see. Okay. We need to figure out what is, actually it is defined, it is a torsion constant. Okay, it doesn't mean anything that we really care about. We need to figure out, we need to find an expression of the period as a function of the number of discs. Now, a little bit careful, when he tells you derive an expression, it doesn't necessarily mean to take a function and derive it. Maybe we'll need to do that, but again, it's not really necessary. I think that what he means here is take this rule that is given, 2 pi root of moment of inertia divided by the constant k, and produce another expression that contains the number of discs. Now, the moment of inertia for one disc is 1 over 2 mr squared. But if we bring more discs, then we need to multiply this by the number of discs. So I think that the only thing that we need to do is replace, wherever we see the moment of inertia, replace 1 over 2 mr squared divided by the constant k. Now, there are not too many things that we can do here. The only thing that we can do is bring the r out of the root. So the period of the pendulum is 2 pi r root of mass over 2k. And I think this is our final answer. We need the period as a function for n. I made a mistake here though. I should have multiplied by the number of tens. So here we have the number of tens. And this is our final answer, that the period is 2 pi r multiplied by the root of the number of tens times the mass of its disk, divided by 2k, which is what we need. And the potential energy stored in the torsional pendulum is given, 1 over 2 k times the displacement to the power of 2. This is very, very similar for the potential energy by the spring, which was 1 over 2 k times x squared. I'm just saying. On the following graph, we need to sketch a graph of the, that's a little bit important, of the maximum kinetic energy with respect as a function of the number of tens. All right, now the kinetic energy and the potential energy, we know that they are changing. However, in this case, the kinetic energy, the maximum kinetic energy, and the maximum potential energy is equal to the total energy. The maximum kinetic energy happens when the potential energy is zero. So the maximum kinetic energy is equal to the total energy or the mechanical energy. And this mechanical energy, we know that it remains constant. So when he tells us draw a graph of the maximum kinetic energy, all he needs us to do is draw a line that doesn't change the value, that is kept constant. And again, we don't need to justify this, so my explanation is not really necessary, but let's dig into this a little bit more. Again, the kinetic energy as the object is turning, as the pendulum is turning, changes. Like there are positions where the kinetic energy is zero, and there are positions where the kinetic energy is maximum. But in every case, this depends on how much we are turning the pendulum, and this has a definite value that doesn't really change. So by adding more disks, the pendulum will be a little bit slower as it turns, so the kinetic energy of each disk will be less, but because we have more disks, the total value of the kinetic energy will be the same. And again, this is explained by the kinetic energy max, which is equal to the mechanical energy, and this is constant. So we don't need to say anything else here. And the important part comes here. Now, I believe that we will need the formula that we proved in part A, so let me copy and paste it. Usually when we have a graph of period, or not of period, but any graph, it will be associated with a rule that is presented or proved in previous parts. And indeed we have the period and the root of n here. So let me write the rule as a direct approach for this. It is 2 pi r root of mass divided by 2k multiplied by root of n. So we're trying to bring the rule in a form that has one variable on the y-axis is equal to something multiplied by the variable on the x-axis, and in this case the value on the x-axis is the root of the number of turns. Sorry, the root of the number of disks. This is the representation of the rule, and first part we need to draw the best fit line for this data. The best fit line is a line that connects, that passes through these points, and a little bit careful, it doesn't necessarily pass through the origin, and I don't think that in this case it will pass through the origin, because we cannot really achieve a line that passes between all these points. So I expect that it will be a line that will pass close to the origin, and some of these points will be a little bit above, and some of these points will be a little bit below. So somehow like this, approximately. So this is the best fit line, and in the previous, for this application, we have the radius r as a given, the constant for the pendulum k also given, and from this we need to find the mass of a single disk. Now, it is very, very important to write the rule one more time. So 2 pi r root of m over 2k multiplied by the root of n, and represent the value of y over x, or in this case t over root of n, as one quantity. So t over root of n is equal with 2 pi r root m over 2k, and this part here is the slope. So the slope of this graph will be equal with 2 pi r root of m over 2k. So before we do anything else, we need to stop and find the slope, and we remember that the slope is rise over run. And a little bit careful, we need to find any 2 points on this graph that belong exactly on the grid, on the lines of the blocks, on the lines of the graph. One point that I see, and it is almost clear, is this point where the period is 0.2. And another point that I see is this point here, where the period is 0.6. So we'll go somewhere and we'll say that the slope is rise, which is 0.6 minus 0.2. For the equivalent values on the x-axis for this, the run is, now the value here is 2/5 of 0.5 between 2 and 2.5, so here is 2.2, and there it is 0.8, so 2.2 minus 0.8, so from this we bring the value of the slope, which is 0.4 divided by 1.4, so it is 0.2286, and now it will be easy to find the value of the mass, so 0.286 is equal to 2 pi, the value of the r is given, 0.2, root, the mass is what we need to find, divided by 2k, so 2 times 1.6, so 3.2. Now, first thing that we'll do is divide by 2 times pi times 0.2, so 0.4 pi. The result is 0.227 is equal root of mass over 3.2. Then we need to square this. So to the power of 2, this brings 0.052 is equal mass over 3.2. And if we multiply by 3.2, we bring that the mass is approximately 0.165, so 0.17 kilograms. And this is the answer for part C2. Now we go to the theoretical part of this question, which is that the student finds that the value given by the manufacturer of the disc is less than what we have found. Determine a source of experimental error. So the real value of the mass is less than what we have found. One thing that we could have done wrong is measure the period wrong. There is no way we can measure the number of turns wrong. Maybe not measure exactly the radius of the disk, or the value for the constant k of the torsional is correct. So one of these three could be wrong. We could say determine a single source. So when we measure the period, there could be an error in the measurement of the period. Indeed, if we can see that the period and the mass are proportional, not directly proportional, not linearly proportional, but they are proportional. So if we measure more period than the real value, then the mass will be having a greater value than the real value, and in this case the mass of the disk is less than the value that is determined by the experiment. So maybe there could be an error in the measurement of the period. Specifically, we could measure maybe the student measured a greater period than the real value of the period. And we proceed to part D, where now the student repeats the experiment, but the two disks have a density that varies as a function for the density. Now, let's stop a little bit here and explain what this means. Like before, each disk had a uniform density, so if we could distribute the mass in this disk, we could have a uniform mass, approximately the same mass in all of its area, in all of its surface. Now, for this disk, we have a density that depends on the radius. So, with more, as we go away from the center of the disk, actually not the radius, the r is the distance from the center. So as we go away from the center of the disk, the mass increases. So there is a relatively small mass close to the center, or even zero mass close to the center. Then the mass increases, and then the mass becomes very, very dense, and far away at the very, very edge, the mass is extremely great. So basically, we can see that there is more mass on the edge of the disk with respect to the mass at the center of the disk. So this is before, and this is after. Now, this brings a change in the moment of inertia. For the uniform disk, the moment of inertia is, as we probably know, 1/2 mr squared. Now here we don't really have to calculate the moment of inertia, but because more mass is at a distance greater away from the center of the disk, this will increase the moment of inertia. So the moment of inertia after is greater than the moment of inertia before. So the new moment of inertia is greater. And we need to figure out what will be the result in the slope. Now, from what we understand, the slope is what we proved, but it also depends on the moment of inertia. So I think I will bring the original form for the moment of inertia. Actually, the new moment of inertia doesn't have the slope, so let's bring this part. We said that the slope is 2 pi r root of m/2k. And let's see how this affects our experiment. So would the slope of the best fit line for this new data will be greater, less, or the same with the new density? Now, this affects the moment of inertia, this change affects the moment of inertia, more mass is distributed away, so because the radius, more mass is distributed away, so the distribution of the factor r times root of m for the new part will be greater. So the mr squared for the new distribution will be greater. And since there is a greater distribution for the mr squared, then the root of m times r will be greater. So this will result in a new slope. So we need to mention that the moment of inertia increases, or the factor of root of m times r increases, and this increases the slope. And finally, for one disk, the maximum angular speed is found to be omega u. Okay, for the uniform, I believe, for the uniform disk, okay, it's omega uniform. Again, for one disk, the maximum angular speed for the torsional pendulum is omega for the non-uniform. And which one is the relationship for the omega, for the angular speed between the uniform and the non-uniform disk? Again, if we remember the kinetic energy, and again we remember that the maximum kinetic energy remains constant, it is 1 over 2 I times omega squared. So since the new the new non-uniform disk has a greater value of I, of moment of inertia, and the kinetic energy remains constant, it makes sense that the omega for the non-uniform will be smaller. So the best answer is the first one. However, in order to justify the answer, either we will explain this with words that the kinetic energy remains constant, the new moment of inertia increases, so this will result in a smaller omega, or because it is constant, the 1 over 2 I uniform times omega uniform will be equal to 1 over 2 I non-uniform times omega non-uniform. I forgot the square here. Now the 1 over 2's cancel, so the omega uniform to the power of 2 divided by the omega non-uniform to the power of 2 is equal to the I non-uniform divided by the I uniform. This is greater than 1, and this means that the omega uniform is greater than the omega non-uniform, which is our final answer. I think this is the last part. On the next video we'll go to question 3. I hope you enjoyed this answer. If you have any comments, feel free to express them. Keep studying, and I hope to see you soon. Take care. Thank you for watching.